Let us look at another example of linear programming using graphical method. In a manufacturing process, the final product has a requirement that it must weigh exactly 150 pounds. The two raw materials used are A with a cost of $4 per unit and B with a cost of $8 per unit. At least 14 units of B and no more than 20 units of A must be used. Each unit of A weighs 5 pounds while each unit of B weighs 10 pounds. And we are being asked to determine how much of each type of raw material should be used for each unit of final product in order to minimize the total cost. So let us first understand this example in detail. Suppose this is the final product. We have been given that the weight of the final product must be exactly 150 pounds. So weight is equal to 150 pounds. Now this final product is made up of two raw materials, A and B. So let's say this is each unit of raw material A and this is one unit of raw material B. So both of these combine to make the final finished product. Now we have been given that the cost of A per unit is $4. Now please note that the cost is given in per unit terms, and this per unit could be anything. It can be a box, it can be a carton, it can be a block, anything. So the cost is equal to $4 per unit. And for B, the cost has been given as $8 per unit. Now again, the unit is a generic term, so one unit of A may not be the same as one unit of B. Next, we have been given that at least 14 units of B must be used. So the quantity should be greater than or equal to 14 units of B. And for A, the maximum quantity should be 20. So quantity for A should be less than or equal to 20. Also, each unit of A weighs 5 pounds. So now we are defining what does this per unit mean. So for A, one unit is 5 pounds, and for B, one unit is 10 pounds. So this unit here is 10 pounds. Now with this information, we are being asked how much of each type of raw material should be used for each unit of final product in order to minimize the cost. So how many units of A and how many units of B should be used to manufacture one unit of the final product so that the cost of the raw materials can be minimized. So now in order to convert this into a LP model, the first step is to decide the decision variables. So here we are being asked to determine the quantity of raw material A and quantity of raw material B to be used to manufacture the final product. So let's assume that X is the number of units of raw material A and Y is the number of units of raw material B. Here X and Y are the decision variables. Now the next step is to determine the objective function. Now the objective here is to minimize the cost of the raw materials A and B. So let's say C is the overall cost and we have to minimize it. Now the overall cost will be equal to the cost of A plus the cost of B. Now let's first take the cost of A. So per unit, the cost of A has been given as $4. So for 1 unit, the cost is $4 for this is for A, and we have assumed the quantity as X. So for X units, the cost is how much? So let's say this variable is X1. So cross multiplication X1 multiplied by 1 is X1 is equal to $4 multiplied by X. So the variable is 4X basically. So C is equal to 4 times X plus, now same way the cost for B. So for each unit for B, each unit costs $8. So 1 unit costs $8, and we have assumed a quantity of Y for B. So Y units will cost how much? So let's say this is X2. So cross multiplication again, X2 is equal to 8Y. So 4X plus 8Y. So this becomes our objective function. Now the next step is to determine the constraints. Now the first constraint that has been given to us is that the final product should weigh exactly 150 pounds. So the final product, say this is the final product, this should weigh, each unit should weigh 150 pounds. Now the final product is an addition of the weight of A plus the weight of B. Now the weight of A is the number of units multiplied by weight of each unit. So for A, the number of units we have assumed as X. So for A it will be X and multiplied by the weight of each unit of A. So the weight of each unit of A is 5 pounds. So this is 5. Again the same way for B, we have assumed a quantity of Y units for B. So this is Y multiplied by the weight of each unit. So each unit of Y weighs 10 pounds. So this is 10. So our first constraint becomes 5 times X plus 10 times Y is equal to 150. Now the next constraint that has been given to us is that the quantity of A should be less than or equal to 20. So X should be less than or equal to 20. The next constraint that has been given to us is that the quantity of B should be greater than or equal to 14. So Y should be greater than or equal to 14. And of course, the universal constraint for linear programming models is that X and Y should be greater than or equal to 0. So this becomes our linear programming model. Now let's try to solve this using the graphical method. Now as shown in this figure, let's assume that x-axis represents the quantity of raw material A, while the y-axis represents the quantity of raw material B. Now we are considering the first quadrant of this graph because the value of x and y should be greater than or equal to 0. Now let's first plot the constraints. In order to plot the constraints, we'll drop the inequality signs, and so our equations will become 5x plus 10y is equal to 150, x is equal to 20, and y is equal to 14. Now to plot these lines, we need the x and y intercepts. So let's derive the x and y intercepts for these equations in order to plot these lines. So the first equation is 5x plus 10y is equal to 150. Now let's first put x is equal to 0. So we'll get 10y is equal to 150, or y is equal to 150 divided by 10, or y is equal to 15. Similarly, if we put y is equal to 0 in this equation, we'll get 5x is equal to 150, or x is equal to 150 divided by 5, or x is equal to 5 3s are 15, so 3 and then the 0. So for this line, the y-intercept is 15 and the x-intercept is 30. Now the next equation we have is x is equal to 20. So this becomes the x-intercept. Now x is 20 and it doesn't have a y-intercept. That means this line is parallel to the y-axis. The third equation is y is equal to 14. So again, this equation does not have an x-intercept, or this line is parallel to the x-axis. So let's now plot these three lines. So the first line that we'll plot is 5x plus 10y is equal to 150. Now this line has a y-intercept of 15 and an x-intercept of 30. So let's draw this line. So this line represents 5x plus 10y is equal to 150. The next line we'll plot is x is equal to 20. So this line represents x is equal to 20. The next is y is equal to 14. So this line represents y is equal to 14. Now let us look at where does the feasible region for all these three constraints lie. So the first equation is 5x plus 10y is equal to 150. So that means the feasible region for this equation is the line itself. So all the points on this line would be the feasible solution for this constraint. Next is x is less than or equal to 20. So for this line, all the points on this direction should represent x is less than 20, and all the points on this line represents x equal to 20. The next is y is greater than or equal to 14. So for this constraint, this line represents y is equal to 14, and all the points above this line on this direction would represent y is greater than 14. So based on this line, the pink line, all the points above this pink line and on this pink line are feasible for the equation y is greater than or equal to 14. And for the red line, all the points on the red line represent the feasible solution for this constraint. So if we take these two, basically all the points on this line 5x plus 10y is equal to 150, which are on or above the pink line, represent the feasible solution for these two equations. Now if we take into consideration the third constraint, that is x is less than or equal to 20, again it also satisfies the same condition, that is all the points which are above the pink line and on the red line may represent the feasible solution region. So if we consider these 2 points here, let's say this is A and this is B. So let us now try to find the coordinates of A and B, and then we'll substitute these into the objective function to find out which of these points gives us the optimal solution. So for point A, we can easily find the coordinates. It is on the y-axis, so x-axis is 0, and it hits the point 15 on the y-axis, so the y-coordinate is 15. For point B, we need to solve the two equations, y is equal to 14 and 5x plus 10y is equal to 150. So we can do it here itself. 5x plus 10y is equal to 150. Substituting y as 14, so 5x plus 10 multiplied by 14 is equal to 150. 5x plus 140 is equal to 150. 5x is equal to 150 minus 140, 10. X is equal to 2. So the coordinates of B become 2, and of course y is equal to 14, so 14. Now let's try to substitute these values of x and y to find the optimal solution. So let us first take the coordinates of point A, which are 0 and 15. Now our objective function is c is equal to 4x plus 8y. So if we substitute the values of x and y, we get 4 multiplied by 0 plus 8 multiplied by 15. This is equal to 0 plus 8 5s are 40, 4 carry over, 8 1s are 8, 9, 10, 11, 12. So 120, this is equal to 120. Now let's take the second point, which is B, having coordinates 2 and 14. Let's substitute these values in the objective function. So c becomes 4 multiplied by 2 plus 8 multiplied by 14. This is equal to 8 plus 8 fours are 32, 3 carry over, 8 ones are 8, 9, 10, 11. So this becomes again 120. So the cost at both coordinates A and B is the same, which is 120. Now let us analyze this a little more. So this was our graph. We had a line y is equal to 14 and another line which was x is equal to 20, and the third line which is five x plus 10y is equal to 150. Now based on our earlier analysis, we had this constraint on the left hand side. For y we had constraint on this side, and for this line, that is 5x plus 10y is equal to 150, the solution was the points on this line. So based on our earlier analysis, we had considered the line from point A to point B as our feasible solution region. So this line here was our feasible solution region. Just now what we did is we took the coordinates of these edge points, that is A and B, and we tried to see which one gives us a optimal solution. Now if we try the other method, which is the plotting the objective function line, which is represented as c is equal to 4x plus 8y. So if we convert this in the form y is equal to mx plus c, where m will be the slope, so let's say 8y is equal to c minus 4x, or y is equal to c by 8 minus 4 by 8x. This is equal to c by 8 minus 1 by 2x. So here the slope is equal to minus 1 by 2. So if we start drawing these parallel lines for the objective function, you will note that the lines will be parallel to the line 5x plus 10y is equal to 150. One of the lines will be on top of the constraint 5x plus 10y is equal to 150. So this will be the line which will represent the objective function. To prove this, let's calculate the slope of this line 5x plus 10y is equal to 150. So 5x plus 10y is equal to 150. Let's convert this in the form of y is equal to mx plus c. So 10y is equal to 150 minus 5x. Y is equal to 150 by 10 minus 5 by 10x is equal to 15 minus 1 by 2x. So here also the slope is minus 1 by 2. So basically the lines 5x plus 10y is equal to 150, and one of the parallel lines representing c is equal to 4x plus 8y will be the same lines. And what that means is that our feasible solution region was A to B, the line representing A to B, and the objective function will be on top of this. That means that all the points between A and B represent the optimal solution. Now it is definitely easier to find the coordinates of A and B, and either one of these can be taken as the optimal solution. So we can have optimal solution as x is equal to 0 and y is equal to 15, or x is equal to 2 and y is equal to 14. Again, these are the only two coordinates that we can easily find, but there are multiple optimal solutions for this example.